polynomial rings. And Albert Garreta will give the presentation.
Do we have a clicker? Or?
Yes.
Thank you. Oops. It doesn't have laser? Okay. All right. Okay, thanks. It's a pleasure to be here and present this work we have been working on for some time now. So what we do here is we study the problem of arithmetizing and proving computations that are unfriendly to finite fields. And by this I mean, for example, classic hashes like SHA, ECDSA, SHA, Ketchak, Blake, hashing and then signing the digest like SHA plus ECDSA, lattice operations, and others. I'm not going to spend time motivating this problem. I think it is quite known that these type of computations are hard to write over a finite field in two senses at least. One, in the sense that it is hard to actually encode the operations that happen in these computations as finite field operations, like it's conceptually hard to do. And the other is that when you get to do it, like when you are finally done, you end up with a computation, like a circuit that is sometimes much larger than the size of the computation you wanted to prove to begin with, in some sense. OK, so I mentioned finite fields and SNARKs over finite fields. What we do here is, instead of working with finite fields that we do, we also work over polynomial rings, fx, qx. So fx denotes the set of all polynomials on one variable x and coefficients in f, a finite field. And qx is the same thing, but coefficients in q, the field of rationals. We also work on finite fields and integers and rationals. OK, so this Zinc Plus thing is a framework. It consists of several components. One is an arithmetization system, which we call Universal Constraint System, UCS. And in terms of the syntactic shape of the constraints, it handles the type of constraints we are used to, like R1CS, CCS, error, lookups, and others, like permutations and so on. All of them expressed over these rings I mentioned. And then there's also another interesting thing, in my opinion, in UCS, which is that we not only have polynomial expressions of the input and the witness that are equalities to 0. We have polynomial expressions of the input and the witness that, instead of being equal to 0, is like they belong to an ideal. And I'll give examples, so it will be more clear what I mean about this. OK, another component of the framework is a method for building PIOPs for UCSs from finite field PIOP. So it's a compiler that takes finite field PIOPs and builds a PIOP for UCS. And to build SNARKs, we follow the PIOP plus PCS paradigm. So we also need a PCS. And note that these constraints in here, as I said, they are over those rings, which means that, in particular, the witnesses are vectors of elements whose entries are on those rings. And this means that our PCS has to be able to handle this type of witness vectors. So we choose hash-based approach. And as all good hash-based PCSs, there must be a linear code beneath them. And this is fine when we are in fx or finite fields, but it gets trickier when we are in qx and q, because then we need a linear code over the rationals, and there's not that many known options. So we designed this new code that we call integer pseudo-Reed-Solomon code. It's MDS, so it has best possible distance, like Reed-Solomon code, and it's a foldable code, so it has FFT-like encoding procedure, which is more or less as efficient as Reed-Solomon encoding. And they are not Reed-Solomon codes, strictly speaking, and that's why we call them pseudo, and we'll see why. And then we also instantiated the framework. So framework is provides many ways to, it can be instantiated in many ways. We instantiated it in a way, and then we arithmetized SHA-256 hashing, several chains, plus ECDSA with this UCS constraint system and benchmarked the results. And yeah, we expect these numbers to get better because there's optimizations that we have planned and features that we haven't implemented yet. OK, so let's look at the components. So the arithmetization. Instead of defining what a UCS is, I'll just take a toy function and arithmetize it in our style. And hopefully, that will be clearer than an abstract definition. So let's take the following function f, which maps 32-bit integers to 32-bit integers. And what it does is you take the integer a, you square it modulo 2 to the 32, and then you do bitwise AND with the initial integer. So this function is interesting because it's like a toy, it's like a proxy function for things that happen, say, inside SHA-256. SHA-256 has some substeps that sort of look like this. OK, so let's start with some observations. Let's say we have four binary polynomials of degree less than 32. And we look at them over Qx or Zx, not over any field. Then we have that this very simple linear constraint written over Qx encodes or arithmetizes XORing and AND of the polynomials. Like XOR and AND of bitwise polynomials has the obvious definition of coefficient-wise XOR and coefficient-wise AND. And regarding squaring mod n, another observation, if we have two 32-bit integers, we can write the constraint u is the square of v modulo 2 to the 32 over q or qx by adding an extra term, like adding a multiple of 2 to the 32. OK, so there's squaring modulo 2 to the 32 and XOR and AND, which over Qx, if you assume you have binary polynomials and 32-bit integers, are very simple to write down as linear constraints. And these are two of the building pieces of the function f. But there's one important missing piece here, which is that, OK, now we can, for example, square a, our input, modulo 2 to the 32. But now we have to do the AND with a. But this, if we use this trick in here, our square, u, is an integer. And in here, we need to have binary polynomials to use this trick. So now we need a method for moving from integers to their binary representation in binary polynomial form. So first, we established this bijection, which is binary representation of integers. So if you have a 32-bit integer, you can represent it as a binary polynomial where the coefficients are the bit decomposition of the integer. And as a map, it acts as if you have a binary polynomial, you evaluate at 2, and then you get the integer represented by the binary polynomial. OK, so we also arithmetize this bijection given a binary polynomial u and a 32-bit integer v. We have that u2 is v, so u is the binary representation of v, if and only if u minus v belong to the ideal generated by x minus 2 over qx. So if you know commutative algebra, u minus v belongs to the ideal means that u minus v is 0 modulo x minus 2, which is equivalent to saying that u of 2 is v. Membership to x minus 2 means this holds if you replace x by 2. OK. So this is enough to arithmetize this function with 3 linear constraints and some constraints on your witness, u we ask that our witness, parts of our witness are binary polynomials, and then we have 3 linear constraints that arithmetize this function f. Okay. And there's many things I would like to talk about UCS that I will not in the interest of time. Okay, so now I guess this looks quite nice, but then the question is, can we prove this? Because, okay, maybe I convince you that the arithmetization system is very expressive, but if we cannot efficiently prove anything that is expressed in this arithmetization, then it's not very interesting at the end of the day. Okay, so let's discuss how do we prove UCS statements. First of all, let's say that we have that our UCS looks like this. We have just an R1CS as usual, and instead of having R1CS equals 0, R1CS expression equals 0, we have R1CS is contained in an ideal. ABC are the R1CS matrices, and Z is the concatenation of the public input and the witness. Okay, so the typical thing you do, I'm just gonna do the typical thing you do when you want to prove R1CS, but I'll have some ideals bothering me around. So what I'm gonna prove is that some polynomial belongs to the ideal for all element in a hypercube. In a normal situation, I would be the 0 ideal, so I would have QBZ equals 0. And this Q is this, the polynomial you get by plugging in the multilinear extensions of the matrices and Z. And now we have this lemma that says that QBZ is in the ideal for all elements in the hypercube, if and only if it is in the ideal for a random C. The reason this holds is because this is basically Schwarzschild lemma for rings. If this thing belongs to the ideal for all the hypercube, for all B in the hypercube, if this thing is 0 in the ring you get by quotienting by the ideal, so you use Schwarzschild lemma in the quotient, and that's it. So this gives us a first step, which is the verifier sends a random evaluation point, and the prover sends the evaluation at this point, y, which is a polynomial, and the verifier checks that this y is in the ideal, and the result, like now the constraint that QZ is in the ideal for all element in the hypercube, is replaced by a single strict equality. So the for all quantifier has disappeared and the ideal has disappeared. Now we have a single polynomial equality over QX. And if you replace I by the 0 ideal, you get just the first step of Spartan that we are all familiar with. Okay, so now we have this. Now we have to prove this. We have reduced the for all in the hypercube belongs to the ideal to a single equality over QX. So one thing we could do, this constraint here, the QCZ equals Y looks like a Spartan-like constraint. Now we could just follow a Spartan-like protocol and start running sum checks over QX, but that is not very appealing because sum check over rationals grows. The integers grow non-stop, and also we are in QX, so there are several coefficients. It doesn't sound great. So what we are going to do now is we are going to project this equality to a random finite field, following the lead of the Zartan protocol. So what happens now is the verifier samples a prime Q and an element in a finite field of Q elements, and we apply this projection from the ring QX to the field, which consists of you reduce everything modulo Q and replace X by alpha. Okay, I'm ignoring a technical issue here, which is that not all rationals can be reduced modulo Q, but you can show that with high probability all the rational, when you sample Q randomly, all the rationals can. So let's just pretend that all rationals can be reduced modulo Q. Okay, and then as a result, you get an R1CS-like constraint over the random finite field, where your witness is a projection. The witness in this R1CS-like constraint is psi of z, which is the projection of your initial witness in this finite field f. And now in here, we just use any PIOP you like over the finite field, like Spartan. And at the end of the day, you are left with MLE evaluation claims for the projection of the matrices and projection of Z, of the witness and the public input, which we will now prove with a PCS. And this is the cost of doing this PIOP step. I just explained a breakdown of the costs. There's a small optimization I didn't mention, which is that reduction modulo Q can be done at the beginning of everything before you do the ideal check, which allows you to compute the element Y modulo Q, which is cheaper. Okay, so before discussing PCSs and IOPPs, I want to talk about codes over Q, and then we'll discuss PCSs depending on the time. So, by the way, this whole protocol, I describe it for QX, but you could also do FX. So integers and rationals are not super important in this framework. If you don't like integers and rational, you can ditch them and still use these ideas about the ideals and so on. And for some computations, it's completely fine. If you only want to prove SHA-256, you might want to do it over fx for f, say, 64, like a Goldilocks field, or a bit smaller, a smaller field might do. For some, there's some advantages of using Q and Z, but I'm just saying that this framework is not married to integers or rationals. But anyway, if you want to use integers or rational, you need a code over those. And the code we use, we call it IPRS codes, and we have an ambitious wish list for it. We want it to have optimal distance, like Reed-Solomon codes. We want the encoding to be efficient, and we want to avoid something, an issue that is easy to encounter, and I'll discuss it next. So in a finite field, a Reed-Solomon code satisfies this wish list, but in Q, it's not as clear what is available. So an initial attempt to getting such a code would be, for example, to just use a naive Reed-Solomon code over the rationals. And by this, I mean the code formed by the evaluations of polynomials over the rationals. So this would be MDS. It might have efficient FFT, depending on efficient encoding, depending on how you set it up. But the issue is that the code words are gigantic, like they have gigantic entries, because you are evaluating a polynomial of degree D, which usually is like 1,000,000. So your entries in the code word might be 1,000,000 bits long, not good. So another idea is use the following observation, which is, say you have a prime field F, and you have a code and a generator matrix M for this code over F. And now you define a code over Q, which is just the set of vectors you get by multiplying M by vectors, okay? And you don't do any modular reduction. And here you look at M as a matrix of integers instead of a matrix of field elements. And you can show that this code has at least the same minimum distance as the original code and the same dimension. So we could just lift a generator matrix of a Reed-Solomon code, and this is what we will end up doing. But the question is which one? Because the most obvious one, the van der Monde matrix, is not a good candidate. By the way, this approach gets rid of the norm explosion, because you can always take M to have all entries reduced modulo Q. If you take an M where all entries are reduced modulo Q and you lift it to Z, when you encode, your code words won't be gigantic in bit size. So yeah, lifting the van der Monde matrix, which is a generator matrix for a Reed-Solomon code, would lead to small norm, optimal distance, but over the integers or rationals, that matrix doesn't have an FFT structure. It's unclear whether you can encode efficiently with that matrix over the integers and rationals. So what we do is a middle ground. We use the lemma, but we use it in a different matrix. And to find the matrix, we take an FFT algorithm for a Reed-Solomon code over a finite field, and we leave the algorithm to Z, or the rationals. As I said, we are just applying the previous lemma, but for a different matrix. So yeah, we fix an FFT algorithm over the field. We execute it over Z, which means that we never do modular reduction, except that we use Twiddle factors and the base matrix elements reduce modulo Q. And if you set up the FFT algorithm correctly, you end up with code words that are not very big. The encoding process is an FFT encoding process, so the code is a foldable code, actually. And you get MDS code. You get an MDS code. And these are the costs we have for our PCS using these IPRS codes for the application I mentioned. I don't have exact benchmarks, but it looks like encoding for these IPRS codes has a similar cost as encoding for Reed-Solomon codes over, say, Goldilocks field. So properties is that these are not Reed-Solomon codes. The code words are not evaluations of polynomials. That's why we call them pseudo. They have MDS distance. They have norm bound, like they have practical norm bound. In this application, we have a norm growth of about 40, 60 bits. And the encoding time is nice. OK, and the PCS. Again, we work on FX or QX. I'm going to discuss QX, but again, the framework doesn't necessarily need to use Q. So our goal, as you saw, was to commit to multilinear polynomial, F, with coefficients in QS. I will explain what this D and B are doing here in a moment. And at the same time, we want to prove evaluation claims for this multilinear extension projected onto some field. And now, what is this D and B? So this D and B weren't there before, so I skipped some theory, or I skipped some things. So to guarantee the soundness of the PIOP, we need to assume that provers are using witnesses or polynomials with entries of bounded bit size and bounded degree. And we delegate proving this to the PCS. So I didn't write it before, but we do need it, so I'm writing it now. OK, so let's say we already have a hash-based PCS over Q, and let's see how we build a hash-based PCS for this setting. And what we do is pretty simple. There's nothing too mysterious here. We just write the multilinear polynomial we're interested in as a sum of multilinear polynomials with coefficients in Q times powers of x, and we batch commit to these FIs. And this sounds scary because in our applications, D, the degree is 32. So here we are committing. In our applications, these FIs are binary, and there's 32 of them. And that sounded scary, and it was one of our main questions. Will this be too expensive? And it turned out it wasn't. We exploited the fact that these FIs in our applications are binary. We used a SIMD approach to make it pretty efficient. And now we know that the evaluation claim for the original polynomial can be written in terms of the FIs. So now you can batch proof evaluation claims for these FIs again, and this batch proof gives you the evaluation claim for F. And now we assume we have a hash-based PCS over Q. Now the question is how we build it. Also, if you don't want Q, if you are working on FX, here you are done, because you would assume you have a hash-based PCS over a field, like your favorite hash-based PCS, and you follow this recipe, and that's it. You are done. If you want to work on Q, now you have to build a hash-based PCS over Q, which I'm not going to describe. It is breakdown-like. If you are familiar with the previous work called Zinc without a plus, it is very similar. We proved better security properties for it, and we proved it round-by-round knowledge sound. We can use better mutual correlates agreement error bounds, and so on. There are some nuances. If you are projecting onto, say, a binary field, like F, a field of size 2 to the 128, then it actually gets tricky to prove those claims efficiently. So that is a non-obvious thing. But other than that, if you are projecting into a prime field, it's pretty much a breakdown. It's pretty much what we did in our previous work. So I'll skip it. And that will be all. Thank you.
Questions?
Thanks for the talk. Can you clarify something about the F we saw towards the end about for your code? So there are two funny fields, right? Mm-hmm. So one is the one you're going to use for the code, and another is the one, I guess, coming out of what the verifier is sampling.
Yeah.
Is it true there are two of them? What's the relationship between these two?
For the purposes of the code, we don't need the code to. The code only needs to have good properties over Q. Its properties never come up in the random finite field.
No, okay, sorry. What is F you're using for the code? So the F.
Okay. Yeah. The code we live from is not related to the field the verifier samples. So we pick in our implementation we pick 2 to the 16 plus 1 field for the IPRS code. So we picked an FFT algorithm on this Fermat prime, and we lifted it to the integers. And this Fermat field doesn't have anything to do with the field sampled by the verifier.
Mm-hmm. What is can I ask a second? Sorry. What is the main contributors of to the proof size?
It's the PCS. The PCS contributes as if there was no arithmetization gain or little arithmetization gain from UCS. Because we are batch committing to the vectors of coefficients.
Right.
And there's 32 of them in
right.
This.
So it's a number of bits of, in a sense, it's related to a number of bits of the.
Yes.
Yeah. So I see. So when you go to, you're working on, when you say the integers at the beginning, you meant integers, 32 bits integers, right? And so that's correct, right? When does that show up at the beginning?
Well, in general, the framework doesn't need to.
No, yeah, 100%. I mean, but there's going to be this linear dependence to the number of bits.
Yes.
Okay.
Yes.
Yeah. Thanks.
Okay. Thanks for the talk. Had a question. We've been proximity prize and IOPPs and all that. I was wondering, do you have to prove sort of correlated agreement for this code that you created?
That's actually, thanks for the question. So we prove.
This is not staged, by the way.
Yeah. We are using the 1.5 Johnson bound for this code. It's a linear code. We extended the Katham, had as a result to the rationals. It's just the same thing, but we just wrote it on the rationals. So we use the 1.5 Johnson bound. We have no idea if these codes have a mutual correlate agreement up for higher distances. But it would be nice to know. And yeah, there's other interesting question about this code, which is what happens if you look at the code modulo a bigger prime? Like say you want to encode something over a field of size 2 to the 56, and you don't want to pay the blowout cost of 2 to the 56 bits, and you decide to use something like this, because you can also lift the FFT algorithm to such a field. But we don't know if if they have good correlate agreement then, and we also don't know the minimum distance. Wait, scratch that. We do know they have 1.5 Johnson bound, but we don't know the minimum distance.
There is time for a short question.
So you described the protocol for one ideal membership. Can I have multiple different ideals?
Yeah, you can have multiple ideals.
Yeah, and how do I sort of glue them together, like the relation?
So once you have done the first step, where the verifier sends an evaluation point, the prover sends the y. You remember the y?
Mm-hmm.
So it sends the y for each ideal, and at that point there's a bunch of R1CS-like constraints that are strict equalities over QX.
Oh.
And now you batch them in your next sum check.
Okay, thank you.
Okay, let's thank Albert again.